So good morning and welcome everyone. I think this is lecture number 8. I'm not mistaken. Tell me what we were discussing in the last class.
Average life.
Average life. Okay. Do you remember the terms that we use and the formulae that we discovered? What was the first formula of radioactivity that we discussed? Tell me. What was the first formula? Again, if you have to go back in the past, that is not a good sign. That means you have not studied what was done in the previous class. What was the first formula? Problem. As I told you, if you come to the next class without studying in the previous class, this class goes down the flush. So I'll give you 5 minutes again. Unless and until you understand what we have done in the previous class, this class is useless. Go through the previous class and tell me what did we do. What was the first formula? What was the first thing in radioactivity that we discussed? You have to know it.
Equation of alpha decay.
What?
Equation of alpha decay, sir.
Alpha decay. Okay, that was not the question that I asked. I asked you what is the first equation in radioactivity that we discussed. Radioactivity, what was the first thing that we discussed in the previous class? It seems that you don't have any clue. We discussed the rate of decay minus dN by dt, and we saw that it is directly proportional to the number of active nuclei present. Do we remember this?
Yes, sir.
Second formula. What is the second formula then? We will remove this proportionality sign, and in the place of proportionality sign, what will come? See, you have no idea of what I'm talking. Absolutely no idea.
So.
Okay, idea has started to come. Minus d by n by dt will be equal to lambda n. Do we all remember this?
Yes, sir.
Okay, sir. What is this lambda known as?
Decay constant.
Decay constant. It has got other names as well. Decay constant is one of the most commonly used. Then we had the formula where we had n, the number of nuclei will be n naught, where n naught is the original number of nuclei, and we had a formula. What was that formula?
E power minus lambda t.
E to the power minus lambda t. Okay. Then we had a formula of log to the base e. Wala formula in terms of n and n naught. What was that?
Minus lambda t.
What minus lambda t? Log to the base of e of what?
N by n naught
N by n naught
equal to minus lambda t.
is equal to, oops, not e. I've written e wrongly. Is equal to minus lambda t. Are we all remembering these formulae, or they are going above our heads saying bye bye, we are going? We will not be able to catch us. We remember these formulae, yes or no?
Yes, sir.
Next one, half-life. Half-life. What was the formula for half-life? T half or TH? T half or TH. What was the formula for half-life?
0.693 by lambda.
0.693 by lambda. We have to remember these formulae because same formulae will be coming in exam straight away. From where this 0.693 was coming, there is also a formula in terms of natural log. What was that formula? What is 0.693 actually?
ln 2 by lambda of E.
ln means log to the base of E. 2 by lambda. That is correct. Okay. Now, from where this natural log of 2 is coming? So, at half-life, what happens is the number of active nuclei n becomes n naught by 2. Do we understand this?
Yes, sir.
So, what I am going to do is in this equation, I am going to put the value of n as what?
n
I
naught
am
by
going
2.
n naught by 2, and there we will get the formula of half-life. Do we understand this?
Yes, sir.
From there I get the formula of half-life, and I get half-life T half or TH as natural log of 2 divided by lambda. Do not forget this ever in your life. Then
Okay,
I
sir.
had a formula for T average or average life. I can also write it like this. T in a dabba means T average or T mean or TA or TM, whatever. What was the formula of T average or T?
TH by 0.6934.
Huh? See, even by reading from your notes, you can't tell me. That is not good. What is the formula for T average?
1 by lambda.
Okay, 1 by lambda. Now there was a relation between this one and this one. What was the relation between this one and this one? See, we have forgotten because we have not noted it down and we are still looking from your notes. And that is the problem with notes. Notes are too much. The sheet that I've given is too much and I asked you to write it. Did you write it then and there itself? Did you care to write it? I don't think you cared. Well, anyways, may God give you enough wisdom that you understand that whatever I am telling you are words of God for you. These are the, I am right now God for you, and whatever I say are words of God. So whatever I say will come in the exam, and that time, please don't blame God that God is not helping you. This was the formula that I was talking about, and that was the last thing that we did in the class. That was the last thing that we did in the class. This is the relation between T average and T half. Do we remember this?
Yes, sir.
Do not forget this. T average is 1.44 times of T half. Will you remember this now?
Yes, sir.
Pakka?
Pakka, sir.
Okay, sir. So I have faith on what you are saying. And with this, we begin the activity for this class. And since I have used the word activity, the next heading that we are going to study is something known as activity or the decay rate. So that is the next heading that you will write, not read from the notes that you have got or the sheet that you have got. That is just for your reference. If you have missed anything, then you look into that sheet. Otherwise, you write it in your notes. Activity of a sample. What do you mean by activity of a sample? Sometimes this activity of the sample is also known as its decay rate. We understand the term activity or decay rates stand for the one and the same thing. Do we understand this?
Yes, sir.
What is this activity or decay rate? It is the rate at which the radioactive sample is decaying. It is the rate at which this radioactive sample is decaying. You can denote it by A standing for activity, or you can denote it by R standing for rate. Do we understand this?
Yes, sir.
we all should also understand this activity or A or rate will be minus dN by dt. Yes or no? It is the rate at which the nuclei is decaying. Do we understand this?
Yes, sir.
Since it is the rate minus dN by dt, and just now we saw that minus dN by dt is equal to lambda, and your activity A or your activity equal to R will be equal to minus dN by dt, and which will be always equal to lambda, and you should never forget this in your entire life. Do we understand this?
Yes, sir. Okay, sir.
That is the one formula for activity that you should remember. The other formula for activity is exactly same as what we had done for the number of nuclei. Remember, the number of nuclei present at any time n is equal to n naught e to the power minus lambda t. Yes or no?
Yes, sir.
For activity, that formula becomes R or A becomes equal to R naught into e to the power minus lambda t. Tell me what does R stand for here? What does R stand for here? This formula is exactly same as n is equal to n naught e to the power minus lambda t. In this formula, what does n stand for?
Number of active nuclei.
Number of active nuclei at this time. Well done. Then what does R stand for here in this formula? Activity of the sample at this point in time. What was N naught in the previous formula?
Initial.
Initial number of nuclei. What is R naught in this formula? It is the initial activity of the nucleus. Is the initial activity of the nuclei. Do we understand this? R does not stand for radius. Radius has got nothing to do here. R means rate. If you are getting confused with R, you can use A for activity. Please don't say RS radius. You will be not sounding good. E stands for the Euler's number. Lambda stands for what?
Wavelength.
Lambda stands for decay constant, and T stands for the time in picture. So this is how both the formulas are related to each other. Do we understand this?
Yes, sir.
Okay, sir. So I'll just rub this formula from here, and then we can understand how this activity depends on, and this is what you will write. Activity of a sample at any instance depends on the number of active nuclei, or R is proportional to N. Do you see this here or not? Do we see this here or not?
Yes, sir.
Whatever is the mass of the nuclei which is present, or whatever is the number of nuclei that is present, activity depends on that term. Will you remember this?
Yes, sir.
Since it is, as you can see here, you can see an exponential relation. R decreases exponentially with time, in the same way as the number of nucleus decrease. Do we understand this?
Yes, sir.
Well done. R is not a constant. As you can see, R depends on time. It depends on N, which is the number of nuclei, M, which is the mass, total mass of the nuclei, and time. Do we understand this?
Yes, sir.
We'll give you a minute to note it down. Have you
Done, sir.
noted down? Have you noted it down? Yes or no?
Yes, sir.
Then again, the same thing that we discussed in the number of nuclear wala formula. At time t is equal to 0. Oops, why is this going here? Okay. At time t is equal to 0, the value of R is R naught. Do we understand this? So initial activity is R naught. At
Yes, sir.
time half-life, this activity will become R naught by 2. We understand this?
Yes, sir.
At half-life, number of nuclei also become N naught by 2. At half time, T half,
Yes, sir. Yes, sir.
activity also becomes R naught by 2. Similarly, for T average, when the time becomes T average, number of nuclei also becomes 37%. Here also you can see the activity becoming 37%. Do we understand this?
Yes, sir.
Now I can make the same formula. I made the formula for number of nuclei. I made the formula for activity. Similar formula can be made for the mass of the total mass of the radioactive substance that is left. M will be equal to m naught e to the power minus lambda t. Do we understand this formula?
Yes, sir.
What does m stand for here?
Mass.
Mass at given time. What does m naught stand for here? M naught stands for the original
Field.
mass. Do we understand this?
Yes, sir.
Okay, this is what you need to remember. The last point is converting grams. Oops. Converting grams into number of moles, and that is more about chemistry. Do we understand this? How you convert gram into moles? They have converted gram into moles, and that is how they have got the activity of the sample. Do we understand this?
Yes, sir.
Okay, so please note down this formula. You don't have to note it down over and over again. You can see that if you remember one formula for number of nuclei, you can make the rest of the formula on your own. We understand this?
Yes, sir.
So we only need to worry about one formula. The rest of them will come automatically. I'll give you a minute to note it down. Please note it down so that I can move further ahead. A or R is known as the activity or the rate of decay or the decay rate. We started with the number of nuclei, then we switched on to the decay rate, and at the end we have seen relation between the mass of the nuclei which is left and the mass of the nuclei which were there in the original condition. Shall we move ahead?
Yes, sir.
Now comes the unit. There are questions which have come directly from this unit. So please remember this unit. The SI unit of radioactive decay is becquerel. Will you remember this? BQ, becquerel. 1 becquerel is equal to 1 decay per second. So if one nuclei is decaying per second, the rate becomes 1 becquerel. Do we understand this? You have to remember this. There's nothing to understand.
Okay, sir.
Other unit is Curie, CI Curie, and 1 Curie is 3.7 into 10 raised to the power 10. Very high number of decays per second. 1 decay per second becomes 1 becquerel. So I can have a relation between 1 Curie, 1 CI, 1 Curie will be equal to 3.7 into 10 raised to the power 10 becquerel. We understand this?
Sir.
Similarly, we have the third unit, which is Rutherford. 1 RD, 1 Rutherford is 10 raised to the power 6 decay per second, which is 10 raised to the power 6 becquerel. Do we understand this?
Yes, sir.
Sometimes they might use the term specific activity, specific activity, specific activity. This is activity of 1 gram of the substance, 1 gram of radium, 1 gram of uranium. So its unit becomes becquerel per gram or Curie per gram or Rutherford per gram. We understand this?
Yes, sir.
So remember, the specific activity, they might ask you a simple question: what is the specific gravity, specific activity, or what is the unit of specific activity? You can write it as Curie per gram or Rutherford per gram or becquerel per gram. Shall we move ahead?
Yes, sir.
Pakka pakka?
Pakka, sir.
Doubt to nahi, sir? Now, the question that comes to you: is this, and we are going to solve this question first. The half-lives of X and Y. X is one nucleus, Y is other nucleus. The half-lives of X and Y are 3 minutes. So one of them, X is having a half-life of 3 minutes. That means in 3 minutes, it will become half of the original value. The number of nuclei will become half, activity will become half, mass will become half. The other one, Y has 27 minutes half-life. At some instant, activity of both the samples are same. Find the ratio of active nuclei. Can you do that for me?
Yes, sir. We will do.
Okay, sir. Your time starts now. What will be the number of active nuclei? Anyone with an answer?
So, N1 is to N2, oh, 1 is to 9, sir.
1:9, sir. That is the correct answer, sir. And these are the type of question that will come in the examination hall, sir. So if you remember if you remember what? The basic concept, you should be able to solve this question. And what is the basic concept of solving this question? Activity of number 1 or X will be equal to lambda X into N of X. Yes or no?
Yes, sir.
Activity of the sample 2 will be lambda 2 into N2.
Yes, sir.
Now A1 and A2 are same. So I equate these two. Lambda, the value of lambda is 0.96 by 3 by t half. We understand this?
Yes, sir.
That's it. We put the value of lambda 1 here, from lambda 1 here. Then I use a different color pen. I put the value of lambda 2 from here to here. We understand this? Yes or no? From
Yes,
here,
sir.
I get this relation N1 by N2 is T1 by T2. From here, I can find the ratio of N1 and N2. Everyone got this? Can I have some raise hand that we got this?
Yes, sir.
Well done, sir. So we are almost at the end of this particular topic. There are some important points that you must remember, because these are the points that normally come in the examination hall as straightforward questions. So I'll be giving you these points. And you must remember this, because a question can come straightforward from this point. You can mark these points and remember them. Now remember, whenever a radioactive substance decays, it may not decay into one, because the intermediate one, for example here, A is getting decayed into B. Do you see this?
Yes, sir.
Now this B substance or B nucleus which is formed, it may not be stable. So what will happen? This B will decay into
C.
C. This C will decay into
D.
D, and so on, unless and until we reach a nuclei which is stable. So this thing will keep on continuing. Do we understand this?
Yes, sir.
Yes, sir. Then, sir, we see, sir, the activity or the stability of D will be more than C, will be more than B, will be more than A. Do we understand this?
Yes, sir.
A is getting decayed into B. That means B is more stable than A. B is getting decayed into C. That means C is more stable than B. C is getting decayed into D. That means D is more stable than C. Do we understand this?
Yes, sir.
Radioactivity order, the order in which they will decay, the rate at which they decay, A will be decaying fastest, then B, then C, then D. Do we understand this?
Yes, sir.
Whenever we end up with a stable element, stable nucleus, lambda will be
Lambda
0
is equal to 0.
and its half-life will be infinite. Do we understand this? For a stable
Yes.
nucleus, half-life is infinite. It will never decay. It will just remain like this. I'll give you a minute to note it down.
Yes, sir.
Have you noted it down?
10 seconds, sir.
Such type of decay is known as successive radioactive decay. Successive radioactive decay. Successive radioactive decay. It means from A, we are not going to get B, because B is getting decayed into C. So it is successive decay. A is getting converted into B, B is getting converted into C, and so on. Do we understand this?
Yes, sir.
But here, my dear friends, one condition will come. And what is that condition? It is known as the condition of equilibrium. Equilibrium. What is the condition of equilibrium? You may have this question in an examination hall. What is the condition of equilibrium? Now see, what to see? See, here we have A getting converted into B. This is A, this is B, and this is C. A converts into B, B converts into C. So now on one hand, I have A converting into B, so B is produced. On the other hand, I have B converting into C, so B is getting reduced. B is getting produced, B is getting reduced. B is getting produced, B is getting reduced. Do you understand this?
Yes, sir.
One hand, A is producing B, other hand, B is producing C. Then tell me, what will you mean by equilibrium? At equilibrium, what will happen is that it's very simple. The rate of production of B becomes equal to the rate of decay of B. Do we understand this?
Yes, sir.
Similarly, rate of production of C will be equal to rate of decay of C. Do we understand this?
Yes, sir.
Rate of production of D will be equal to the rate of
Rate
decay
of
of
decay
D. Do
of
we
D.
understand this?
Yes, sir.
Please note this down. Then what will happen? Therefore, the number of active nuclei of B or C or D will become constant. Do we understand this?
Yes, sir.
And therefore, the activity, since it is dependent on the number of nucleus or nuclei, the activity also becomes constant. Do we understand this?
Yes, sir.
Please note it down. I'll give you a minute to do this. And we have this tremendous formula that we are going to discuss just now, because on this concept you might get a straight away direct question, and you will be one of the very few students who would have done this, and you will get an edge in the examination. All, have you understood the concept of radioactive equilibrium? We call it radioactive equilibrium. Have you understood the concept?
Yes,
Have you
sir.
understood the
Understood.
concept of radioactive equilibrium? Yes or no?
Yes, sir.
Yes, sir. Then, sir, this will be happening at the radioactive equilibrium, sir. That at radioactive equilibrium, R1, which is the activity of 1 or rate of 1, will be equal to R2, will be equal to the rate of R3, will be equal to the rate of R4. Yes or no?
Yes, sir.
N1 lambda 1 will be equal to N2 lambda 2, will be equal to N3 lambda 3. Yes or no?
Yes, sir.
And from here, I can put the values of all these things. N1 into lambda 1 is equal to N2 into lambda 2. From here, I can find the relation between N1 and N2. Yes or no?
Yes, sir.
Yes, sir. When I get lambda 1 here, lambda 1 is 0.693 by T half. So I get lambda 1 here and I will get T half here. Yes or no? If
Yes,
I
sir.
just remember this equation, which equation? Equation number 1, I will get to this equation number 2. Yes or no?
Yes, sir.
This is what you got to remember. Equation number 1 and equation number 2. If you can remember equation number 3 and equation number 4. Equation number 3 is relating the mass of 2 in terms of its molecular mass. They have just converted mass and number of nuclei into molecular mass. Do we understand this?
Yes, sir.
Is anyone having doubt? Please raise your doubts now. Else you just note down the formulae, because the question that comes in the examination all will be straightforward from this formula booklet. Do we understand this? Can I have some raise hands?
Yes, sir.
Girls, are we there in the class? Okay, I'll give you a minute to note this down. Shall we move ahead in life?
Completed, sir.
Well done, sir. Then comes this very important series. You may not note it down. We can just read it from your booklet. That is why this booklet is given to you. The radioactive series, and many times, many questions have come on this radioactive series. Now, there are 4 types of radioactive series. One is known as the 4N series, 4N plus 1, 4N plus 2, 4N plus 3. N standing for integer. You can see this 232 is divisible by 4. Yes or no?
Yes, sir.
And that is why this series is known as 4N series. This 4N series starts with thorium. Thorium 232 and 90. It starts to decay, and the stable product is lead 208, 82. Do we understand this? So you have to remember each and every series, the starting product and the end product. This is what you have to mug. Do we understand this?
Yes, sir.
You may not note it down. You can mark it in the book and you can read it from there. Then we have 4N plus 1 series, Neptunium. It starts with Neptunium 237, 93 and ends on bismuth 209, 83. Do we understand this? Then we have 4N plus 1 series, which is uranium U238. It ends on lead 206. Actinium series, which starts with uranium 235 and ends on lead 207. You may not note it down. You will have to remember it by heart. It. Can you do that for me?
Yes, sir.
Yes, sir. That will be of great use, sir. Because, sir, the question will come straight away from the theory part, sir. Most of the cases. And they are giving this question on radioactive series. I'll give you a minute. Shall I move ahead? Tell me when you are done, so I'll move ahead. You have to remember the original product, original nuclei, and you have to remember the N nucleus with their atomic number and your mass numbers.
Okay, sir.
Shall I move ahead?
Yes, sir.
Then again, nothing to note down here. You will have to see it from your booklet, and that's why the booklet is here. What are the radioactive isotopes in human life? What are the uses in medicine? That is what you are going to use. Testing of blood circulation, brain tumor, thyroid testing, cancer cure, and blood cancer cure. I'll give you a very nice example. Yesterday, I was talking to a friend of mine who is Ayurveda doctor. He was a batchmate when I was in 10th standard. Ayurveda doctor. I mean, it's easy to become an Ayurveda doctor right now. He's in a small place in MP, and he has got his own radio. This lab. He hires it from somewhere. He's giving that lab 4 to 5 lakhs rupees per month, and he is earning a lot, and he's just an Ayurveda doctor. He has this radioactive lab which he hires, and he pays that lab only for the testing part. All these tests, 5 tests, 6 tests, and he pays them 5 lakhs per month. So imagine the amount of money he is just making from these testing. Do you understand what I'm going to say? Do you understand what I'm saying here?
Yes, sir.
Even if you become an Ayurveda doctor, which is the lowest in all those ranks, you are going to mint a lot of money, and people will respect you a lot. Okay, so these are the examples in medicine. In archaeology, we can find out using carbon dating and to find the age of earth and meteorites. Question on this may not come to you. In most of the cases, the question will be coming in from the part A. Do we understand this?
Yes, sir.
Again, you will have to remember these points. I can't help you in remembering them. The only way I will tell you is make a list, keep it close to you wherever you can see it. The third type of use is in agriculture for protecting potato from earthworm, artificial rains, and as fertilizers. Again, this might not be so useful to you. The point that is going to be useful to you is for medicine. Do we understand this?
Yes, sir.
Please note it down. I mean, you don't have to note this down. You have to just mark it in the booklet, and you should remember it. Remember, the most important point for you is point number A, the use of radioactivity in medicine. Can we move ahead?
Yes, sir.
Now, we have seen alpha decay, we have seen beta plus decay, we have seen beta minus decay, we have seen gamma decay. Yes or no? Do we remember them?
Yes, sir.
There's also one more type of decay. If you want to call it decay, you can call it decay. In this decay, what happens? This is known as the K electron capture. K electron capture. Now, K stands for the K shell, and K electron obviously stands for the electron in the K shell. Do we understand this?
Yes, sir.
Now, what happens in this K electron capture is in K capture, we call it K capture. K capture, a nucleus captures one of the inner orbital electrons. Ooh. So this electron is moving in the K shell, and this nucleus is going to capture it. And a proton transforms into a neutron. Electron gets captured, and proton converts into a neutron. Hence, K capture is like positron decay. N by P ratio increases because neutrons become more and proton become less. Do we understand this?
Yes, sir.
And there is a vacancy in the K shell. Electron will transfer from higher shell into the K shell and X-ray would be emitted. So X-ray
Yes,
will
sir.
also be emitted in this case. Do we understand this?
Yes, sir.
And sir, the last point is the most important point, sir, where we have this equation, nuclear equation. This gentleman over here is your parent nucleus. Do we see this?
Yes, sir.
Then I have an electron which is being captured from the K shell. Do we understand this?
Yes, sir.
And here a proton gets converted into a neutron. Therefore, the atomic number decreases by 1. Do we understand this?
Yes, sir.
Then we have this radiations coming out from where these X-rays are coming. From where these X-rays are coming. From where these X-rays are coming.
From electrons.
From the electron transition that takes place from higher shell to lower shell, electrons will be transferred, and that is how these X-rays would be emitted. Do we understand this?
Yes, sir.
What type of X-rays it would be? Continuous, characteristics, which one? We've already done X-rays. Which type of X-rays would be there? Continuous or characteristics? Again, you've forgotten it. Well, God help you. Please note this down. I am not going to tell you the answer, which type of X-ray is produced. Because if I keep on telling you the same, which one?
Characteristic X-ray.
Good, good. Now you remember. See, that is the power of the brain. If it gets stressed, it will start to remember. If I just tell you the answer, you will forget it. Sorry, and I'll give you a minute to note this down. This is the most important thing that you got to note down.
Okay, sir. Done, sir.
Done, sir. Then, sir, sorry, sir, we will solve some questions, sir. Is it okay, sir? Do we have the permission to solve the question? Yes or no?
Yes, sir.
Then, sir, this one, sir.
Option A decreases by 4.
Ah, that's how I want you to answer. Fast. Fast. Now that's going fast. Okay, that's great. I don't have to tell you what is happening here. So I'll move on to the next one. All these are from your AIPMT. AIPMT is your NEET. It was tougher at those times. This one comes next. Aha.
Option C.
Option C. So fast calculations. Are you reading the answer that answer sheet, or you are solving it, bacha? You have already done that.
I have solved yesterday, sir, this question.
Well done, sir. Option C. So how do you do it? Tell me for the rest of them. Half-life is given, yes or no?
Yes, sir.
77 days is the half-life. What is the decay constant? So we have to just write the formula. What is the formula? Lambda is equal to 0.693. You can just write it as 0.7 divided by T half. Yes or no?
Yes, sir.
Put the formula, get the answer, stay happy. Do we understand this, everyone? Can I have some raise hand from everyone?
Yes, sir.
Not one, everyone. Everyone is there?
Yes, sir.
All of you have done this sheet? Most of you have done this sheet?
Not all questions, sir. Only direct
Not see, no matter. If you have done even 5 questions, that is good, bicha. If you have even done 5 questions, that is good. I cannot do 110 questions in the class. You can understand. I am only going to do selective ones that revises the entire topic. What is the answer for this one?
Alpha rays.
And towards which side they will deflect?
Negative side.
Yes, sir. That is how we understand the point, sir. That is how we solve the question, sir. Now this question, sir, because activity we did not do, so probably you would not have done this question, sir. So this is coming on your screen, sir, right now, sir. Here, sir. Let's see who does this. In a radioactive material, the activity at time T1 is R1 and a later time T2 is R2. This is how the questions are framed. This is how the questions are going to come. If the decay constant of the material is lambda, then question number 14.
Option A.
Option A is the correct answer. How did you get it? How did you get it? Because this is looking like the because I see negative here, therefore I have given the answer as this. Now this is not the way you should be giving answers. Okay, now remember here, this is time T1. How would I would have done it. This is time T1. This activity is R1. So this becomes my initial time. Do we understand this?
Yes, sir.
And this activity becomes my final activity. Do we understand this?
Yes, sir.
So I have a relation between initial activity and final activity. Final activity R2 will be equal to initial activity R1 into e raised to the power minus lambda into how much time I have taken. The time I have taken is T2 minus T1. Do we understand this?
Yes, sir.
That is the original relation. That should be the relation. But here, the relation is not given in terms of R2, the relation is given in terms of R1. So what do? I take the entire equation on the left hand side. E goes and gets divided here. And we do simple maths. Then I will have R1. If I just increase the size so that I can write more. Are you getting my point, bacha? What I'm saying here, are you getting it?
Yes, sir.
This is the original condition. If I write from this original condition, I can write R1 will be equal to R2 divided by E. Instead of writing it as divided by E, I multiply it by E and I write lambda into T1, T2 minus T1. Do we understand this? How I've written this?
Yes, sir.
Now you look at this one and you look at this one. Are both of them same? Yes or no? Option number C is already gone. Option number D is already gone. The only competition is between option number A and option number B. So the correct answer is option number A. Everyone got this?
Yes, sir.
Shall I move ahead in life?
Yes, sir.
Then I will solve this question, sir, for you, sir. Question number 17, sir. Tell me the answer, sir. Remember the neutron to the proton ratio. Uh-oh. Neutron to proton ratio? What is this? Let's see if you can do this for me. This is AIMS 2005. I'll make space. How will you get the number of neutrons, first of all? Any idea how will you get the number of neutrons? You have to find the neutron to proton ratio. How will you get that? You can see 238 here. What is 238? What is 238, bacha?
Proton plus electron.
Proton plus neutron. Yes or no?
Yes, sir.
What is 92 here? Number of protons. Yes or no?
Yes, sir.
How do I get the number of neutrons? I subtract 92 from 238. Yes or no?
Yes, sir.
So that is how you get the number of neutrons. From the mass number, you subtract the atomic number. But I have to find the proton to neutron or neutron to proton ratio in the product nucleus. So first of all, I have to find the... Yes, beta?
Nothing, sir. Sorry.
First of all, I have to find out the product. It is emitting 8 alpha particles. So the mass number will go down by how much? 8 alpha particles. Mass number will go down by how much? 32. Yes or no?
Yes, sir.
So what will be the new mass number? 238 minus 230 minus 32. 206. Yes or no?
Yes, sir.
What will happen to the atomic number? In an alpha decay, mass number goes down by 4. What happens to the atomic number? Increases or decreases? Increases. No. Yes? Yes or no?
It decreases, sir.
Mass number decreases. Sure. Mass number decreases. Sure. Atomic number decreases. Sure.
Yes, sir.
By how much?
Mass number decreases by 4, atomic number decreases by 2.
Great. What happens in beta negative decay?
Mass number is constant.
Right.
Atomic number increases by 1.
I hope you are not getting confused, bacha.
Yes, sir.
Are you getting confused? See, that is the problem. If you don't remember it, you will get confused. In beta negative, mass number remains same and the atomic number increases by 1. Yes or no?
Yes, sir.
Now, can you give me the answer for this one, sir? So, when I emit 8 alpha particles, atomic number will get down by how much? 8 into 2, 16. Yes or no?
Yes, sir.
But it will emit 6 beta particles, so it will increase by 6. Yes or no?
Yes, sir.
8 into 2 is 16. It will decrease by 16 but increase by 6. So it will decrease by 10. Yes or no?
Yes, sir.
So the new number would be 82. Yes or no?
Yes, sir.
206 is the 206 is the 206 is the mass number and 82 is the atomic number. Can I have some raise hand that we understand this from everyone? Now you can find the number of neutrons. How many number of neutrons are there? 206 minus 82. What is that number? (206 minus 82).
124.
124,
sir.
124. Is that so? So 124 is the number of neutrons, 82 is the number of protons. Now you can find the ratio and the correct answer is This is the number of neutrons. This is the number
62
of
by 41.
62 by 41. So you will have some questions where you will have to spend more time in calculations. Do we understand this, bacha, everyone?
Yes, sir.
Do we understand this, everyone, bacha?
Sir.
Anyone having any doubt?
No, sir.
No, sir. So, sir, all types of question come. Some questions you might have to spend more time in calculation. Some question you will have to spend less time in calculation. Therefore, if the question is straightforward, you must be able to answer it in very less time. For example, this one, again, this is again from AIMS, same year AIMS. In a radioactive material has a half-life of 10 days. What fraction of material would remain after 30 days? How will you do this? Getting confused? Half-life is 10 days. How much will remain after 30 days? Any idea?
No, sir.
So how are you going to solve this question? I'll give you another formula, and that is why I have done this question. One more formula. Number, this is not in your sheet. Number of nuclei after n, small n, number of half-lives. Half-life was a very famous game when I was of your age. I told you about that, right? Yes or no?
Yes, sir.
Now, after one half-life, and I have half-life, I will write it as T half. Okay. After one half-life, what is the number of nuclei I have? N will be equal to N naught by 2. We understand this, yes or no?
Yes, sir.
Now you will apply some brain, sir, and give me the answer, sir. After two half-life, it will become half of this, yes or no?
Yes, sir.
Half of this is half of N naught by 2. Half of N naught by 2 becomes N naught divided by 2 raised to the power 2. Do we understand this?
Yes, sir.
Well done, sir. Then after 3 half-life, how much nuclei will be left? 3 half-lives have gone.
N
How
naught
much?
by 8, sir.
Well done, sir. Do not call it N naught by 8, sir. Call it N naught by 2 raised to the power 3, sir. That is better, sir. Yes, sir, or no, sir?
Yes, sir. Okay, sir.
Now, if I just make this equation long and if I ask you what is the number of nuclei remaining after n half-life, what would be your answer, sir?
N naught by to the power of n.
N naught by 2 raised to the power of n. Now, can I come back to the question, sir? Will you be able to solve it now, sir? Shall I come back to the question, sir? Yes, sir. No, sir. Better I go, sir. You tell me, sir. Shall I come back to the question now, sir?
Yes, sir.
No, sir. Yes, sir. The question is here, sir. Here comes the question, sir. A radioactive material has a half-life of 10 days. What fraction of the material will remain after 30 days? After 30 days, how many half-lives have gone? How many half-lives have gone? One half-life is 10 days. In 30 days, how many half-lives are gone?
3.
3. 3, 3, 3, 3, 3. So what is the answer? My n will be equal to n naught divided by 8. Yes or no?
Yes, sir.
So my fraction n divided by n naught, that is a fraction, it becomes 1 by 8. Yes or no?
Yes, sir.
What is the answer now, sir? 1 by 8 is the answer, sir. Which one is 1 by 8? Yes, sir. Which one is 1 by 8, sir?
C, sir. 0.125.
0.125, sir. That is the answer, sir. And that is how you do it. Will you remember the formula, the new formula that I made for you, especially for you?
Yes, sir.
Yes, sir.
Yes, sir.
I'll do one more question, sir, because most of the questions are in the same category. Will you be able to solve the rest of the question on your own, bacha?
Yes, sir.
Again, see, 2005 the question came, 2006 the question comes. That means this is a very favorite topic of NEET. Question will always come. Today you have U 238, 92 has Falana and Dhimaka.
Option B, sir.
Option B, sir. Correct, sir. Good, sir. This is how you should be solving the question, sir. The question which is straightforward should be given in a flash. Do everyone understand this? Yes or no?
Yes, sir.
Good, sir. I will just do one more, sir, so that you understand. Okay, you have not understood nuclear fusion and fission, so I can't do this. I can't do this. Okay, I'll do this one. Let's see, because this is somewhat different. So I'll just do this. I'm looking for different questions so that I cover each and every question. This comes, sir. This comes. Let's see what is the answer, sir. This question also involves chemistry because you have to know what is Kr and what is Sr. What is Kr? I don't know.
Krypton.
What is Sr? Krypton, right?
Yes, sir.
And what is Sr?
Strontium.
What is the atomic number of Kr and Sr? I don't know them. Because in one, atomic number is given as 26 and the other is 36, 38. So if you don't know the atomic number, you cannot solve it. But let us see who can do this. This is an atomic reaction. This is a nuclear reaction. Remember, mass number should be same, atomic number should be same. Do we understand this? Yes or no? Tell me now.
Yes, sir.
Yes, sir. Atomic number here is 92, sir. On the left hand side, on the right hand side, we have 56, sir. So what will be coming the atomic number, sir? That gives us the answer, sir. Yes, sir, or no, sir?
36, sir.
36, and only one option is 36, sir. So the answer is what,
Option
sir?
is B, sir.
Answer is B, sir. Do we understand this?
Yes, sir.
So I'm trying to solve all the questions that can come, different types of questions. This is one more AIPMT 2000. In the given reaction, what is the particle X?
Neutrino, sir. Option C.
Well done, sir. Option, sir. This is how you must solve questions, sir. Fatafat, sir. Not taking much time, sir. Because you don't have that much time, sir. You have to save that time for the difficult question where you have to calculate. One more I'll do for you. This one. So that I am confident that you know the reactions. Yes, sir. What is the answer, sir? 33. Which type of decay?
Beta decay.
Beta minus or beta plus?
Beta minus.
Well done. So it could have two options, beta plus and beta minus. The correct option is beta minus. Anyone understand this? Can I have some raised hands?
Yes, sir.
One last, and then we will move on to the new topic. This one.
Option A, sir.
Z number of protons and A minus Z number of neutrons. You all understand this? We have just done this in the class, right or no?
Yes, sir.
Well done, sir. I'll give you 2 minutes to see what we have done in this entire topic. 2 minutes, and then we will move ahead with the next topic. 2 minutes to go back in the past. Take out your sheet, take out your notes. If there's anything that is troubling you, this is the time that you ask me your doubts so that we can clear them right away. 2 minutes. Go through the entire thing that we have discussed. Anything that I can help you with? Or shall I move forward?
Sir.
Shall we move forward?
Sir.
Yes, sir. Then comes the size of the nucleus, sir. You must know this. There is no way I can tell you how this comes. You just have to remember the formula. The size as a number of nucleons. You understand what is nucleon?
Yes, sir.
As the number of nucleons increases, size will also increase. Yes or no? More nucleons,
Yes,
they will require more size. What is the relation? R, which is the radius of the nucleus, and A, which is the mass number of the nucleus. R is proportional to A raised to the power 1/3. Do we see this relation?
Yes, sir.
The size of the nucleus is in the order of Fermi meters. Remember this, again a knowledge-based question which can come straight away in the examination hall. So I can write this R, the radius of the nuclei, as R naught, which is a constant, A raised to the power 1/3. A means the mass number, and the value of this R naught is 1.2 Fermi meter. Do we understand this?
Yes, sir.
Two things you have to understand. Size of the nucleus is proportional to A raised to the power 1/3, and therefore the volume 4/3 pi r cube. We assume it to be a spherical thing. The volume will be proportional to r cube, so volume V will be coming as proportional to the mass number A. Do we understand this?
Yes, sir.
I've seen straightforward question coming from this topic. Same formula in your examination hall, and if possible you can also see it in the sheet, or we will do it in the class as well. Straightforward question from this. I'll give you a minute to note it down. You will have to note it down. You understand this?
Sir. Done, sir.
Written this down.
Yes, sir.
Now comes simple things that you must be knowing. If you don't know it, you will remember it. Mass of the nucleus. This mass is very small compared to gram of kg. Therefore, it is measured in AMU. Do we understand this?
Yes, sir.
1 AMU is mass of one atom of carbon 12 divided by 12. Do we know this?
Yes, sir.
If I just do the calculation, 1 AMU will come as 1.66 into 10 raised to the power minus 27 kg. Do we understand this?
Yes, sir.
And this is approximately equal to the mass of proton, which is also approximately equal to the mass of a neutron. Do we understand this?
Yes, sir.
Mass of proton and mass of neutron are very, very similar to each other. Note this down. What is 1 AMU? This definition. And how much is the value of 1 AMU? Have you written it, bacha?
Yes, sir.
Now let us talk about the mass of the nucleus as such. Now, mass of a nucleus, what we will do is we have to find the total mass of the neutron, total mass of the proton, add them, and probably we will get the mass of the nucleus. Yes or no?
Yes, sir.
It's actually not that simple. Let us take it for that. And we know that mass of a neutron and mass of the proton are equal to each other. Yes or no?
Yes, sir.
So basically, if I multiply the mass number with the mass of the proton, I will get the mass of the nucleus very,
Yes,
very,
sir.
very near to it. Yes or no?
Yes, sir.
That means mass of the proton is fixed. I can write the mass of the nucleus, m is proportional to A, the mass number of the nucleus. Yes or no?
Yes, sir.
This is one important point that you must know. Remember, radius of the nucleus is proportional to A raised to the power 1 by 3. Volume of the nucleus is proportional to A at mass number. Mass of the nucleus is proportional to A. Are we getting the picture, the bigger picture?
Yes, sir.
It's not as big picture as triple R, but it is also a picture that will matter a lot in your life. Do we understand this?
Yes, sir.
Now, we have talked about the radius, we have talked about the volume, we have talked about the mass. The only thing that is remaining, straightforward question, density of nucleus, rho, mass divided by volume. Mass is proportional to A. We see this, yes or no? Volume is proportional to A. Do we see this, yes or no?
Yes, sir.
Therefore, density does not depend on the mass number. Density of the nucleus is almost constant, and it is 10 raised to the power 17 kg per meter cube. Almost all have the same density. Do we understand this? A very important relation. If they do not ask question on radius, if they do not ask a question on volume, they do not ask a question on mass, and the most difficult question that they can ask is the relation of density. How does density depend on mass number? Straight away we will get the answer, it depends on A, but you can see that it does not depend on A, it is independent of A. Will you remember this fact?
Yes, sir.
Pakka?
Pakka, sir.
Pakka, sir. Okay, sir. Have you noted this down, sir? I'm waiting for you, sir.
20 seconds, sir. Done, sir.
Okay. Then comes the Einstein mass energy equation. You understand mass energy equation? Energy is mass, mass is energy, and E is equal to mc square. You must have read this equation, yes or no?
Yes, sir.
So E is equal to mc square, where m is the mass, E is the total energy, and c is the speed of light. Yes or no?
Yes, sir.
Now remember here, a very important relation. If the mass is 1 AMU, if the mass of the body is 1 AMU, you understand the meaning of 1 AMU?
Yes, sir.
1.67 into something something. Na? Now, if I convert this 1 AMU into energy, the energy that I will get for 1 AMU, if I put the value, it will be 931 mega electron volt. Will you remember this?
Yes, sir.
What, sir? That if 1 AMU of mass is there, 1 AMU of mass is there, the energy you can get from Einstein's equation from 1 AMU of mass is 931 mega Mega means 10 raised to the power 6. Mega electron volts. Will you remember this?
Definitely.
Okay. Please note
Okay,
it
sir.
down. It's a very important result that you must remember. The energy which is equal to 1 AMU of mass is 931 mega electron volts.
That's sir.
Okay. Then we come to the last point of this class. And the last point of this class, I hope everyone is noting it down.
Yes,
These
sir.
are things that you have to note down. That is the only way you remember them. The last thing for this class is the mass defect. Mass defect. Just now I told you the mass of the nucleus is basically mass of neutron plus mass of proton. But that was only half fact. In fact, the fact is, and the fact is on point number 1. Can someone read point number 1 for me? It is on your screen. It is in front of your desk, in front of your eyes on the desk. What
Mass
is
of
point? Read.
Mass of nucleus is always less than the sum of masses of nucleons in it. The difference is called mass defect.
That means if I have 5 protons and 5 neutrons, I find the mass of 5 proton, I find the mass of 5 neutron. But when I put it inside the nucleus, a nucleus which is having 5 proton and 5 neutron will always have less mass compared to the combined mass. Do we understand this?
Yes, sir.
This difference is known as mass defect. Mass is less, therefore mass defect. Do we understand this?
Yes, sir.
Do we understand this?
Yes, sir.
Then I have a simple formula to find out the mass defect. How will I find the mass defect? If the mass of the nucleus is m, mass of the proton is mp, mass of the neutron, almost same but still different, is mn. What will be the mass defect? The mass defect will be simply total mass of proton plus total mass of neutron. This will always be more minus mass of the nucleus. Do we understand this?
Yes, sir.
Do we understand this formula or are you getting confused in this formula?
Understood, sir. Okay.
So this is formula number 2. Remember, in formula number 2, we are using the mass of the nucleus. We are using the mass of the nucleus. In formula number 3, we are taking the mass of the atom. There are two things. One is the mass of the nucleus. The other is the mass of the atom. If I take the mass of the nucleus, the formula is number 2. If I take the mass of the atom, then the formula becomes somewhat different, because if I take the mass of the atom, the mass of the electrons is also added into it. Do we understand this?
Yes,
And
sir.
that is why this mass of the electron wala part comes here. Do we understand?
Yes, sir.
Because in mass of the atom, this mass of the electron is added, so I have to subtract it and whatever it is. That's why the formula looks different. Do we understand this?
Yes, sir.
So we will end today's class with last point, which is the binding energy. Since we have understood mass defect, we have to also understand binding energy. Now, what is this binding energy? We have understood that mass of the nucleus is less than the mass of the constituent nucleons. Yes or no?
Yes, sir.
That means we will require some extra energy to split the nucleus. Yes or no?
Yes, sir.
That energy is known as.
Binding energy.
And how do you find out this binding energy? We'll find out this binding energy by multiplying the mass defect by c square. This much is the mass defect. You multiply it by c square. That is the energy that is holding the nucleus together. You give it that much energy, nucleus is free, and you have a nuclear bomb exploding. We got this?
Yes, sir.
We got this?
Yes, sir.
We got this?
Yes, sir.
I can have one more
Yes.
formula for this. I can write this binding energy as mass defect in AMU multiplied by 931 mega electron volt. You understand how I've written this?
Yes, sir.
One AMU is 931 mega electron volts. I find out how much is the mass defect. I simply multiply by 931 and I get my answer. Correct or not?
Yes, sir. Correct.
This is how binding energy and mass defect are related to each other. In the next class, we'll go ahead and finish off this chapter. There are many things in this chapter that has to be done. If you can do them on your own, it would be very good, because most of the things have to be done by your own hands only. For example, what is a nuclear reactor? If you can just, it's all about reading this. Can you read this for me? What is a nuclear reactor? Before coming to the class tomorrow, what is a moderator? What is control rod? What is nuclear fuel? What is the coolant? Do we understand this? If you can read this small part, it would be very easy for me to continue in the next class.
Okay, sir.
Okay, sir. So we'll finish this topic in the next class. If you have any doubts, you can ask. Else, it's a wrap from my end. Take care and enjoy your life. Bye-bye.
Bye, sir.
Bye.